Assalamualaikum, we are from Group 2, Section 1. We'll present our group project assignment of power quality, which is the title is under voltage, voltage flicker, power frequency variation. So before I continue to the explanation, let me introduce our group members, which are Muhammad Adib Isma, Muhammad Ashraf, Muhammad Luqmanul Hakim, Nur Atikah Adillah, and me, Nur Syazani binti Skimin. For the introduction, power quality refers to the stability and purity of electrical power supply to system and device. It is essential for the reliable operation of electrical equipment, especially in environments with sensitive or high-tech systems. Poor power quality caused by issues like voltage sags, harmonics, and low power factors can lead to equipment damage, energy losses, and operational downtime. Ensuring good power quality improves energy efficiency, reduces maintenance costs, and extends the lifespan of equipment. So, as modern electrical systems grow more complex, maintaining power quality becomes increasingly important for both performance and safety. Under voltage is a sustained reduction in the RMS voltage level below 90% of the nominal voltage for a duration longer than 1 minute. Common causes include overloaded circuits, undersized wiring, faults in the distribution system, or voltage drop due to the long transmission distance. This condition can lead to overheating of motors, poor performance of electronic device, and unintentional shutdown in automated system. In industrial setting, under voltage can trigger protection relays, help production processes, and degrade the equipment life. For the voltage flicker refers to rapid and repetitive change in a voltage magnitude, typically caused by fluctuating or cycle loads such as arc furnace, welding equipment, and large induction motors. These fluctuations usually range from 0.1 to 7 Hz and result in visible flickering of lighting, especially in incandescent lamps. Although not typically damaging to equipment, voltage flicker can cause discomfort, reduce workplace productivity, and generate customer complaints. While for power frequency variations occurs when the supply frequency divides from the system nominal value. These variations are usually due to imbalance between electricity generation and demand. Even small frequency deviation can disrupt timing device, interfere with power conversion systems, and affect the speed of synchronous motors. In severe of cases, prolonged frequency deviation can compromise grid stability and lead to the widespread outage. The objectives for this project are to utilize MATLAB to simulate power quality issues such as undervoltage, voltage flicker, and power frequency variation to understand their characteristics and impacts on electrical system. Next is to analyze and evaluate the effects of this power quality disturbance through detailed case studies focused on undervoltage, voltage flickers, and power frequency variations. Last but not least is to identify, implement, and simulate appropriate mitigation strategies using MATLAB for each specific power quality issues addressed in this project. This flowchart outlines the methodology used for this project, which involves identifying and solving power quality issues using MATLAB simulation. Start, which is the process begins by initiating the project framework. Next is identify power quality issues, which is to determine the common power quality problems such as voltage sags, harmonics, or flickers, which affect the system performance. Next is for the literature review. A detailed review of past research and academic papers is carried out to understand existing solutions and identify gaps. For the proposed solution, based on the literature review, a suitable solution is proposed to mitigate the identified power quality issue. Next is MATLAB simulation setup, which is the proposed solution is then modeled and simulated using MATLAB to observe its performance in a virtual environment. For the simulation success, at this point, we evaluate whether the simulation runs correctly. If no, we go back to analyze the error and debug the model and repeat the setup if necessary. But if yes, we proceed to analyze the simulation results. For the analysis output result, the output from the simulation is then analyzed to determine if the proposed solution is effectively and addresses the power quality issue. Is report writing. After analyzing the result, all findings are documented in the project, and the last process is end, which is it includes the methodology phase of the project. So for the next point, I will pass to the next presenter. Thank you.
Through the implementation of this project, students will implement 3 different types of simulation for power quality issue, namely under voltage, voltage flicker, and also power frequency variation. This aims to minimize operational risk in real-world grid conditions and also meet regulatory and power quality standards. In this project, students will display results for pre-PQ problem case, PQ problem during case, and also post-PQ problem case where to overcome the power quality issue. Students will use the mitigation using by dynamic voltage restore, this datacom average model, and also proportional integral derivative controller methods.
Assalamualaikum, my name is Muhammad Ashraf. I will present the result of our simulation on power quality disturbance, specifically focusing on the undervoltage. For our goal is to analyze system behavior under three key conditions, which is before, during, and after mitigation. Firstly, pre-PQ case. Under normal operating condition, the system receives a three-phase supply of 230 volt at 50 Hz. The waveform is smooth, sinusoidal, and balanced, with a major peak voltage of approximately 328.5 volts. There's no voltage drop during this period. This condition varies that the system is functioning optimally and serves as baseline reference for comparing with disturbed scenarios. In short, this pre-PQ system is stable and meets voltage quality standard. Moving on the second case, a control under voltage was introduced by applying a three-phase fault between 0.1 and 0.2 seconds. It's shown in second graph, which the RMS value is decreased and gain back to normal condition after 0.2 seconds. Based on the simulation data, the peak voltage dropped from 328.5 volt to 255.8 volt, resulting in voltage reduction of 72.7 volt. According to IEEE standard, this qualifies as an undervoltage condition, as the voltage falls below 90% of nominal RMS value. Although the duration is brief, it represents a critical window in which sensitive loads may malfunction if no corrective action is taken. Therefore, this case demonstrates the vulnerability of the system during undervoltage disturbance. After the undervoltage event was detected, the dynamic voltage restorer DVR was activated as the mitigation devices shown in figure 4. Specifically, the DVR began injecting voltage from 3.661 millivolt and continue until 55.97 millivolt, fully within the undervoltage interval. During this period, the DVR supplied a compensating voltage in series with the supply line to counter the drop caused by the fault. As a result, the voltage at a load remains stable and close to its nominal value, despite the disturbance at the source. This confirmed that the DVR successfully maintained the voltage profile by dynamically correcting the deficiency in real time. Instead of disconnecting the load, the DVR ensured uninterrupted operation and protected the system from potential performance degradation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Al-Wisma bin Muhammad Ismail and my number matrix is DE220813. So for my part is we will do a power frequency variations of power quality issue, and in this system we are building a load frequency control. So we have governor, turbine and initial load, and our base power is 250 megawatt and base frequency is 60 hertz. So we will run before we insert the power quality issue. So this graph shows us very stable waveform of frequency and power, which is 60 hertz and 250 megawatt. And then um, we are inserting the power quality issues, which is 50 megawatt. So um, during this issue, the frequency will drop to 59.42 hertz, and the power will increase, but not exactly 300 megawatt. There is 290 something megawatt. 298 298 megawatt. So this is because of sudden load has been injected to the system, and the system is becoming imbalanced. So that's why the frequency has been dropped. So to mitigate this problem, we are using PID controller. The PID controller has been set for the proportional 50, integral 30, and derivative 10. And then we will run the simulation. So this is after we insert the PID controller to mitigate these power quality issues, or which is about power frequency variation. So the frequency has been balanced by the PID controller to 60 Hz, and the power um, has been stabilized to 300 megawatt from 250 to 300 megawatt. This is because the PID controller has calculated the error value, and the output has become the desired value. So that's all for this simulation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Lukmanul Hakim bin Muhammad Arifin, and my number metric is DE220205. So right now I will present about the result for the voltage flicker problem. So for the steady state case, in its initial state, the system is actually function at normal load with no modulation. The variable load remain constant and the distribution statcom operate in floating mode. The programmable voltage source also used to regulate the voltage step, which is we need to evaluate the distribution step reaction. The purpose is actually to see how the system is stabilized when the distribution statcom does not yet mitigate the flicker, and also we need to see how it's just respond to the change of the voltage. So as we can see here, at each scope, the voltage at bus B3 is remain stable at 1 per unit with minimal deviation. As we can see, no noticeable oscillation is present in this statcom current, which is IA statcom. And also we can see the active and the reactive power P and also Q at bus B3 is remain constant. This scenario shows that the system is actually run smoothly and without any flicker related disturbance, because the variable load modulation is actually disabled, and also the voltage regulation stay passive, and also the system is behave normally. So for the next result is the case during power quality problem, which is the voltage flicker is introduced in the simulation. So in this scenario, the variable load is modulated at 5 Hz to simulate the voltage flicker, while the D statcom is in Q regulation mode with the Q ref is set to 0. This means it's not actively yet to compensating the reactive power. So in the scope 1, it showed that the voltage waveform become distorted and also the current fluctuate. This showed that a visible flicker and also the system instability without the mitigation. So for the next scope, Scope 2 is displayed an internal controller signal, which is the reactive current IQ track its reference IQ ref, and also the reactive power, which is Q. It swings sinusoidally with active power remains low and the DC link voltage stays stable at 3000 volt. The modulation index adjusts smoothly, ensuring that the inverter responds passively to load changes. In the last scope, which is scope 3, it shows that the voltage at bus B3 oscillating between 0.96 to 1.04 per unit. The power flow for the P and also the Q and the D statcom current is fluctuate, but the flicker remain high due to the lack of active compensation. So this is the last part, which is the case after mitigation, which is with mitigation the voltage flicker in the system. So in this part, the distribution statcom is switched to Q regulation mode to actively mitigate the reactive power, the voltage flicker while the load continue to fluctuate at the 5 Hz. In scope 1, as we can see, it shows a sinusoidal voltage waveform and a current smooth at 5 Hz current oscillation. This confirms that the distribution statcom is actively compensating the reactive power in real time by keeping the voltage at the bus B3 stable. In the scope 2, as we can see there, the reactive current IQ is closely tracked to its reference, which is IQ ref. The modulation index stays within a safe range of 0 to 1.33 per unit. It varies smoothly, showing that the stable operation and also an effective switching between the capacitive and the inductive mode. The reactive power Q is adjusted up to plus and also minus 2.7 MVA. MVA is showing the fast response within one cycle and the DC voltage is remain stable. In the scope 3, it's confirmed the system level improvement, which is the bus B3 voltage is now stabilized between 0.993 and also 1.007 per unit compared to 4% of plus minus without mitigation. The reactive power and active power is still fluctuate but more smoothly. So it show the distribution statcom current clearly follow the 5 Hz flicker pattern, showing the dynamic and the reliable voltage. This also proved that the statcom effectively reduced the flicker to below plus minus 1% and also perform a real-time reactive power composition. I think that's all from me. Thank you.
In conclusion, through the implementation of this project, students are able to analyze and evaluate the impact of PQ disturbance on electrical system through detailed case study, especially for undervoltage, voltage flicker, and also power frequency variation. This can be proven through MATLAB software simulation that students systematically build to illustrate real-life scenarios where this disturbance occur. Other than that, students are also able to identify, implement, and also simulate appropriate mitigation strategy for each power quality issue stated in this project by using MATLAB software. This is because through the implementation of this project, students will explore how to obtain the best strategy for target reduction that is appropriate for each type of disturbance. Last but not least, the implementation of this project also indirectly prepare students to be better prepared to contribute effectively to the development of high-quality power system that is robust, efficient, and adaptable to dynamic grid conditions. That's all for me. Thank you.